Wonderful. How are you, everybody who is watching this video? I would like to take this opportunity to welcome you into our workshop 15, where actually that will be still moving, will be still continuing on simulating actually the simple automatic system. We can call it just a simple home automation system. And actually we are going to use the electromechanical switches. My name is Olenjolai. It's the first time to meet the work that I'm doing. I thank God by His own grace that He has given me a gift of teaching and a gift of engineering. So I'll be trying my level best to share and to teach you about what I know concerning about the simple or designing or actual simulations of simple home automation system, or you can call it just a simple automation system. And I would like just to tell you that the requirements for these contents are actually have to go through the workshop 12, workshop 13, and workshop 14, where we discuss the theory behind the electromechanical switches and also some other previous workshops. But again, another requirement for these contents is actually you should have a computer, and also you should have an installations of the electronic simulation software, which we call it offline electronic simulation software, which we call it Proteus, which actually that we are going to use to simulate what you've been designing in a sequence of the theoretical workshop. So right now, I would like just to ask you that to stay connected and be the part of this program. And I would like just to tell you that have your computer and let us continue where we ended. Because in workshop 14, we drew the general block diagrams of this simple automatic system. And once we have drew or we have drawn it, then the next step actually that we open the blocks. We opened the blocks and we came up with a schematic circuit diagram. And right now in simulations, we have already implemented the first two blocks. The first one is called DC power supply unit. And the second one, we call it DC or AC load power supply unit. So today we are going to implement the other blocks, or yes, other blocks. The remaining blocks are, the first remaining blocks is actually the digital sensor unit, where we are going to use either a pull-up resistor network or a pull-down resistor network. But for this case, we are going to use a pull-up resistor network, which actually will be working similarly to how the IR sensor used to detect the presence of the obstacle. And the second block that we are going to open, we'll open the block of NPN bipolar junction transistor, the switch, and then afterwards we'll open the block of relay switch. Then finally we'll open the block of the loads. So have your computer, in case that maybe you are watching these contents at the group or at the class, then you can share at least one computer for the two students in order to make sure that every student can practice. So I have some physical students who have joined in this class, and let us appreciate them and appreciate you online. How are you, students? Okay, are you ready for this workshop? Are you ready for workshop 15? Yes. Okay, so let us continue. So this is actual our linear power supply. Just to remind you, this is a AC mains, we call it alternator. This is our first testing point. This the usually it is idle step down transformer, but we have already set the parameters to make it a step down transformer, but usually it is idle transformer. And this is our second testing point. This is the bridge rectifier, and then this it's our third testing point, and this is our third block that called the filter unit. These are our testing points to measure the outputs of the filter unit, and these are voltage regulator unit. This is 5 volt or 5 volt fixed voltage, and this one is 12 volt fixed voltage. And then this is another testing point. This is our fifth testing point, and this is our sixth testing point. We have also LEDs that actually be used as the power indicators to indicate the power. It means that to indicate the actual operations of the power supply. So this one actually is a single power supply. It's a single power supply. These are the two linear power supply, but we have built them in one schematic circuit diagram. So right now, because we have picked all the electronics components, so let us implementing the digital sensor network by using the pull-up resistor network. So the first component that we need a 10K. So we need a 10K. Let us stop some simulation. Then we need a 10K resistor. Then the next components we need push button. So this is the push button. Then let us rotate them. And also let us rotate this pull down resistor. Excuse me. Okay, so I think that I made a mistake in arranging them. Okay, so this is our pull-up resistor. Let's rotate it, and then let's drag to this point. Then the other component say that we have to take a push button, and let us rotate it. I told you that you have to make sure that you do your testing point to point. Then next thing, let us join the pull-up resistor with the push button. After that, we need 5 volt. So we need 5 volt. So we have to take 5 volt from this point. We have to draw 5 volt from this point. So this is 5 volt from our 5 volt fixed linear power supply. And then we need the ground terminal. So it should come to the icon number 8. So this is, we have already implemented the pull-up resistor network. Then if you do remember what you have drawn in the schematic circuit diagram, we had 2 testing points where actually that our point of interest is measurements of the voltage. So this is our first testing point, and this is our second testing point. Again, this is another testing point. So before we interconnect you, because we've already opened the first block, before we connect to the next block, we can run. But our point of focus right now it's actual on the pull-up resistor network. Remember that in case of the digital electronics, pull-up resistor network, coupling capacitors, decoupling capacitors, pull-down resistor network are very important, okay, in context of digital electronics. So, when we simulate, what do you see? So let us try to maximize. Let us select our sensor unit. So these push buttons is the one that which will be changing the states. So right now the voltage across 10 kilo ohm resistor is 0 when the push button is not pressed. And the voltage across the push buttons, which actually replaced physically by using the IR sensor or the infrared sensor, it's 5.01 volt. Then let us change the state. So you can call this 5.01, it's a high state. So it's a binary, it means that its binary bit is 1. Okay? Then let us change the state. So how do we change the state? We have to push, or actually to press the push button, and also we have changed the state. The voltage across R3 or 10 kilo ohm is 5.01, while the voltage across the push button is 0.00 volt. So this confirms the theory that we have learned, okay? Because you have to verify the theory. However, that when we'll be interconnecting or we'll be connecting this digital sensor unit with the NPN bipolar junction transistor, there is a variations of the voltage, and that is it's not actual happens like that in the physical implementation, in hardware implementation, but this happens according to the limitations and weaknesses or faulty of this offline simulation software that's called the Proteus. Are we together? Because you have techie consideration. Then let us stop our simulation. I think that every student, you can stop the video, and for the physical student, you can actually implement. So you can implement what you have. So implement it quickly. Okay, so the next, the first block, it's the NPN bipolar junction transistor switch. We have to go back to the component mode, and then the first component that we need is what? Bias resistor or base resistor, right? So what the value of base resistor that we learned theoretically, it's 1.2 kilo ohm. So 1.2, I say that this is the object selector, work together with, object preview window. So this is 1.2 kilo ohm resistor. So then once we connect it there, so remember that we used to take our output from the pull-up resistor network between the resistor and the push button. Okay? And I told you that whenever you have a design that you want to use a digital sensor, and that digital sensor does not have library, and maybe you try to find some other libraries to add into the Proteus and you fail, or you didn't find it, then you can use this pull-up resistor network to demonstrate how will your system work. Similarly, you may either use the pull-up resistor network, pull-down resistor network. Are we together? Are we together? So where should you use the pull-up resistor network and where should you use the pull-down resistor network? It depends to the operations of that digital sensor. So, so then let us take our the next component. It's our transistor, our NPN transistor. We say that for this design, we are going to use 2N2222 NPN bipolar junction transistor. Okay, so here we have. Then let us join. However, that we'll also need, we have two testing points, if you do remember. The first testing point is we have to measure the voltage across the base resistor. And the second testing point, we have to measure what? Base current. Right? So we have to go to the, we call it to the visual instrument mode library. And once we are there, we have to take a DC voltmeter. This is our DC voltmeter. And then we have to take our DC ammeter. However, that we are going to use DC milliammeter. And if you do remember in previous classes, Pili reminded us, it's DC microammeter. We should not use a microammeter. We should not use an ammeter. We should not use a milliammeter. We have to use DC microammeter. So let us connect it in series. So this is our base. And then let us connect our measuring instrument. So remember that this is actually to measure the voltage across what? Across base resistor. So let us plug this to this point, and then let us plug our DC voltmeter, which actually measure VB, we call it voltage across base. And then so we have this one, these are the testing points, and this is the third testing point and the fourth testing point with regards to 40. This is the testing point for the NPN bipolar junction transistor switch, and this is the second point. But also we need to measure voltage across what? Across base emitter. So let us connect the positive terminal of the DC voltmeter with what? With, let us connect the positive terminal of the DC voltmeter with the base. And let us connect the negative terminal, there's the negative terminal of the DC voltmeter with the emitter of the transistor. Remember to change the type of the measuring instrument to use DC microammeter. Then we need to take the ground because the emitter is connected to the ground. Okay, so after that, we cannot test this part because remember the transistor is not biased. For instance, if you run your simulation, you won't see anything regarding what is the transistor because the transistor is not biased. The transistor did not receive the power. So that's why that you see all the measuring instruments nearby or connected to the base of the transistor and emitter of the transistor, the actual read 0. So you should not claim that you have always, or it means that you can trace this step to step. It depends to the configurations that you are working with. Okay? Okay? Fine. Then let us stop our simulation and let us focus the base or the collector of the transistor. At the collector of the transistor, we have to go back to the component mode, and then we say that we need to have a switch, a NPN bipolar junction switch indicator to indicate that the switch has successfully switched from, means that maybe from cut-off regions to saturation region, or from saturation region to cut-off region. Eliakimu, we are in the class. Okay, so for that case, we say that which type of LED did we recommend that we are going to use? Students, I'm talking to you. Which type of LED did we say that we are going to use to indicate what? To indicate blue. So this is our current limiting resistor. And then once we have it, we need to take a blue light emitting diode. So this is the blue light emitting diode. We can rotate it in this configuration. And then we need also to measure the, especially the base current. So no, the collector current. Okay? But according to the theory of transistor, the collector current is always measured for the small signal transistor, is always measured in terms of 40 milliampere. So right click and then comes to the milliampere. Similarly, the emitter current should also, okay, we didn't measure emitter currents. Yes, we need also to have this one in this configuration. So if that's the case, we can lead this wire and then we can rotate in this system. Then we can drag it and then we have to change the type of the device from ammeter into milliammeter. And then we have to connect it to the ground terminal. Again, so let us connect the DC milliammeter with LED or blue LED, and let us connect the blue LED with 150 ohm resistor. And then remember that we say that this transistor will draw 5 volt. 5 volt from the 5 volt linear power supply. I see just a few students who are doing it. And in case you did it previously, you can take this time to do it, to redo it. Remember, practice makes perfect. You may say that, oh, I did it, so I don't need to do it. Okay, keep it up. Okay, so then for this time, we have finished it to draw the schematic circuit diagram of NPN bipolar junction transistor switch. So we can test. So let us run our simulation. So when you run our simulation, then we see the collector current is 0, the blue LED is off, then the base emitter voltage is 0, the emitter current is 0, the base current is 0, the voltage across base resistor is 0. Why? Because we did not change the state of the push button. So those are the readings when the push button is pressed. So let us release the push button. So when you release the push buttons, you see that our 2 N2 NPN bipolar junction transistor switch is operating in saturation region. Limi, please join with Eliakim there. Why are you getting surprised? Or ask Eliakim to come there. His computer is desktop. Eh? Okay, so Digna work with that and Dan work with Eliakim. And the bags have to be kept away. Why do you put the bags the place where you have to put the computer? Okay, so for this time, so if you press the push button, the transistor turn off or operate in cut-off region. If you press it, then the transistor operate in saturation region. So that is a good step. So we have tested our digital sensor input unit, its work. And also you have tested our NPN bipolar junction transistor switch, its works. But we still have another testing point, if you do remember. And this testing point is actual. We have to measure the voltage across collector emitter. So you have to measure voltage across collector emitter. So this is the DC voltmeter that will measure voltage across collector emitter, or we call it VCE. So we can run our simulation to analyze. So for this time, you can analyze what is happening to the, stop drawing. Remember that when we had the pull-up resistor network itself, like this, whenever we run, or when we run, and the push button is not pressed, the voltage across push button is 5.01 volt. And the voltage across the resistor it is 0 volt. When you press this push button, then you find that it changes. The voltage across push buttons goes to 0, exactly, and the voltage across the 10 kilo ohm pull-up resistor is 5.01. That is in case the pull-up resistor network is itself. Okay? But when we connected the pull-up resistor with the with the NPN bipolar junction transistor, then when we run and analyze, you see that the voltage, what did we expect it to be, the voltage across the push button when the push button is not pressed? Here we expected it to have 5 volt or 5.01 volt. The audience? Okay, so we expected it to have the voltage across push button to be 5 volt or 5.01, right? But because we have interconnected more than, or we have interconnected 2 blocks, then in simulation you experience there is a voltage drop from 5.01 volt up to 1.22 volt. You have to take a note. But remember that this is against the theory. Are we together? When we press the push button, but what did you expect from the theory? When the push button is not pressed because you have infinity resistance, we expected the voltage, or we measured previously, the voltage across 10 kilo ohm pull-up resistor, it should be 0. But right now, the voltage across 10 kilo ohm pull-up resistor, it's 3.7 what? 9. Are we together? Are we together? Yes. So that is against the theory. And you have taken note of them, because if you don't take a note of them, one day you will panic. So that is about the input. So there is a change in case of the input. But we thank God, because the base currents which is actually required to turn on the transistor was sufficient. However, that the voltage, the supply voltage, or the voltage supplied to the base of the transistor is 1.22 volt, while we expect to supply 5 volt. Okay? Okay? So what the voltage across, across the base resistor? The voltage across base resistor, it's 0.46 volt. Then what the base current? And the base current is what? 379 microampere. And then what the voltage across base emitter terminal? The voltage across base emitter terminal, for this case, it's 0.76 volt, which is actual, it's correct, because we expect to measure between 0.6 volt up to 0.8 volt. Why? Because between base and emitter of NPN bipolar junction transistor, we have a diode. And the potential barrier of the diode for the silicon transistor, or for the silicon diode, it's 0.7 volt. So we are trying our level best to transform from the theory of advanced electronic science. Right? That's what I'm trying to connect what you knew and what you expected to know. Then in case of the emitter currents, is what? What the value of emitter current? 15.3 what? Milliampere. Right? Right? Then, let us come to the collector. So for the collector, what the collector current? 14.9 milliampere. And then, the LED is on. This is in case when the NPN or the 2N222 NPN bipolar junction transistor operate in saturation region. But remember one of the mathematical equations that we taught you in basics of electronic science and also in basics of electronics engineering and also in advanced electronic science, we taught you that the collector currents, the summations of collector currents and base current is equal to the emitter current. So you have the base current, the simulated base current, you have the simulated collector current, you have the simulated emitter current. You can prove. Use a simple, it's just a simple algebra. Take collector currents plus base current and equate with emitter currents to verify, to check whether the theory has been verified or not. That's why we say electronics, it's all about numbers. Electronics engineering is all about formula and equation. Electronics engineering is all about diagrams. It's all about tables of results. It's all about graphs. So the issue is not just to simulate. The issue is not just to use the DC voltmeter and the DC ammeter. The issue is to relate what you are measuring in simulation with what you have been learning in theory. That's the great responsibility that a serious technician, electronics technician, or a serious electronics engineer must execute. Are we together? Are we together? So, what did you find after you did your calculation? What did you find? 202. So is the summation of collector currents and base currents equal to the emitter current? Okay, so when you take the base current of 379 microampere and you sum with collector current, which is 14.9 milliampere, and in order to add them, you have to change one of them. You have to change the unit. But according to the theory of NPN or the theory of bipolar junction transistor, the base current is measured in microampere. But this is for the small signal. But for the large signal, the story will change. Then, in most cases for the small signal, the collector current is measured in terms of milliampere, and the emitter current is measured in terms of milliampere. So we have to change 379 microampere base currents into what? Milliampere. When we change 379 milliampere is equal to 0.379 milliampere. So in other words, the base current it's 0.373 milliampere plus what? 14.9 milliampere. Okay? So when you do the summation, the result is 15.279 milliampere. Because the nowadays students, they have a sickness of a unit. They just mention the physical quantities without including the unit. So 15.279 milliampere is approximately equal to a meter current measured in this simulation, which it is 15.3 milliampere. So the DC current bipolar junction transistor equation has been verified, that the algebraic sum of the DC base current and the DC collector current of the bipolar junction transistor is equal to the C emitter current. Are we together? So let us move on. So let us stop our simulation. Now we are going to implement the fifth block. The fifth block is called what? Relay switch, right? So we have to go back to our component mode. So for the online students, you may stop the simulation or you may stop the video and do that calculation and enjoy the mathematical equations of electrons, because you say electronics, it's all about mathematical equation. So let us take our relay. So this is our relay. We are going to connect it across the what? We're going to connect across the we're going to connect it with the collector terminal of this transistor. But before we connect this relay switch, it's better also to discuss one of the theoretical concepts of the load line. Say load line. Say load line. So in the concept of load line, we say that a load line is actually presenting three regions of the bipolar junction transistor. The first region is called the saturation region. The second one is called the active region. The third one is called the cutoff region. Are we together? Are we together? So we can verify also one of the mathematical equations that we learned in load line. Really? What that mathematical equation? We learned that in case of the load lines, or especially for the output of the bipolar junction transistor, we always have a mathematical equation. When the emitter is grounded, we have a mathematical equation that which is VCC is equal to collector current times collector resistor plus VCE. Write down. So that we call it the C voltage, the C voltage bipolar junction equation. The C output voltage bipolar junction equation. So that equation states that VCC, voltage across collector, which is 5 volt for our case, is equal to collector currents times collector resistor plus voltage across collector emitter, which in short we call it VCE. Right? Right? We have taught you to write dictation. So this is simulations with dictation, with engineering dictation. Then, that is the mathematical equation. Then write that at saturation region, at saturation region, VCE should be equal to 0. While IC is equal to IC maximum. At saturation region, VCE, voltage across collector emitter, should be equal to 0. While collector currents must be maximum. That's one of the things that we have to verify in this simulation. Right? Right? Are you done? The second switch operation equation or operations condition, then write at cutoff region. At cutoff region, VCE is maximum. So you write VCE is equal to VCE maximum. VCE is equal to VCE maximum. And remember that CE should be subscript, and the maximum should be a subscript of 40 of CE. While IC is equal to 0, collector current is 0. Others are writing, you get surprised. Write down. There's no time you say I'll write later. Are you done? So okay, according to our design, what the value of VC? So write the value. VCC is equal to what? VCC is equal to what? 5 volt. Right? VCC is equal to 5 volt. Okay? Okay. So according to our design, remember that when the push button is not pressed, then for that case, the transistor operates in which state? If the push button is not pressed, the transistor operates in saturation region. In saturation region. So in saturation region, theoretically, VC is equal to what? VC is equal to what? Speak loudly. VC is equal to what? 0 volt mangoes. You see, you still have the same sickness. 0 volt. Say 0 volt. 0 volt. And what the expected value of collector current? Maximum. Right? So what is our maximum collector current? 14.9 milliampere. Write it. IC maximum is equal to 14.9 milliampere for this design. Okay? So according to this simulation, what is VCE? What the voltage across collector emitter? The voltage across collector emitter is measured by this DC voltmeter, which is 0.53 volt. What is the value? 0.53 volt. So the simulated value does not agree with the theoretical value, because you say that at saturation region, the VCE must be equal to 0. You are learning theory, and then you want to do practical while you forgot every theory. So we are done with saturation region. Right? Right? Then let us go back, or let us change the state. Let us bias the transistor to operate in what? Cutoff region, where the theory told us or taught us at cutoff region, IC or collector current should be equal to 0, while VCE is maximum. So let us analyze in this simulation. So now the transistor is operating in cutoff region. Then what is IC? Collector current is 0 milliampere. It's true, right? And then what is our voltage across what? Collector emitter, VCE. It's 5.01, which is maximum value. So it is true. Are we together? So the theory or the simulation confirmed the conditions or the theoretical condition for the cutoff region. But for the saturation region, there's a variation. Are we together? Good. So let us move to the next part. So you can see that how electronics is broad. You can have one circuit, and actually you can learn it within even 2 weeks. Just you're still learning one circuit, and you are still learning about what is going on within. Okay, so right now we have our relay switch, but also we need a flyback diode. So a flyback diode, we have to pick 1N4007 NPN general purpose diode. So here it is, and then let us rotate in this configuration, and let us plug our relay switch at this point. Okay? According to the overall schematic circuit diagram, the cathode of this diode is connected with coil number 1, and the anode of this flyback diode is connected with coil number 2. Are we together? Are we together? Then we say that if that the case, this one the coil number 2 and the anode of the diode should be connected to the collector of 2N2222 bipolar junction transistor. Right? 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 Oh, it's not right. It's right. Okay. And then this one should be connected to what? Should be connected to 5 volt DC. Limi, go and dress yourself there. There's the tap. Go there, dress yourself, and then come back quickly. Did you have any testing point between or here? We didn't have any testing point here. But if you're interested, you can measure maybe maybe let us say, okay, let us have another testing point. So you have DC what? You have DC voltmeter. So we can measure the voltage. Supply to the OT, supply to the relay, voltage across the primary or the relay coil. So let us run our simulation at that point. Let us change the state. So if we change the state and examine. So we change the state, nothing is happening to the relay. You see? Hello? Look please, stop drawing, look there. From the theoretical concept that we have learned, we say that if a relay switch receives a trigger voltage or a particular trigger voltage, then it's going to turn on the contact, right? So at this point, before we connect the loads, we can check whether our relay switch is working or it's not working. At these times, when the push button is pressed, our transistor is operating in cut-off region, where collector current is 0. And if the collector current is 0, then there's no triggering to the OT, the relay switch. But if we release the push button, then the transistor, the NPN, the 2N222 NPN transistor will be operating in saturation region. So the transistor will turn on, we have collector current, actually it's going to trigger what? The relay. Are we together? So for that case, we say that, right now, let us release. So when you release, we analyze that our 2N222 NPN bipolar junction transistor is operating in saturation region. But the relay did not turn on. Why? Because remember that for the relay, this is common. Say common. Say common. This is coil number 1. This is coil number 2. This is common. And this is normal open. Say normal open. Say normal open. And this one, we say. And this one, it's normally closed. So when the transistor operates in saturation regions, we expect the pole to move from normally closed to normally open. Right? But right now, it doesn't work. Why? There is a reason. What the reason? The reason is this one. When you go back, let us stop the simulation. Let me give you the reason. When you go back to the component mode and we go back to the Proteus library, then we write relay. So when you write relay, we just have then select switch and relays, then relays as generic. So this is our simple relay. But that simple relay, remember that we learned the different relay switch have different triggering voltage or trigger voltage, DC trigger voltage, right? We have a relay switch which its trigger voltage is 3 volt. We have a relay switch which the trigger voltage is 5 volt. We have a relay switch which the trigger voltage is 6 volt. We have a relay switch which trigger voltage is 8 volt. We have a relay switch which the trigger voltage is 9 volt. We have a relay switch which the trigger voltage is 12 volt. We have a relay switch which the trigger voltage is 15 volt. We have a relay switch which the trigger voltage is 18 volt. We have a relay switch which the trigger voltage is 24 volt. Engineering is all about numbers, right? I like to mention numbers. And when you sleep, tell your neighbor, when you sleep tonight, tell your neighbor, when you sleep tonight, make sure that you dream the engineering numbers. Don't dream snakes and lions. that are chasing you. Okay? Are we together? So this is another key concept that you have to note for the proteas. In physical relay switch, we have different relay switch which the trigger voltage range from 3 volts to 24 volts physically. But in terms of this simulation proteas library, we don't have something like that. So in library of proteas, we just find a single simple relay switch which its trigger voltage is 12 volts. Are we together? You will never find a trigger, maybe a relay switch in proteas of 3 volts or 5 volts or 6 volts or 8 volts or 9 volts or 15 volts or 18 volts or 24 volts. But you can also simulate, or you can implement your simulation, and with the particular relay it means you can implement your simulation with a relay switch and with its particular or respective trigger voltage. Are we together? So remember that the relay switch found in libraries of proteas has a trigger voltage of 12 volt, and that 12 volt it's the default value. So when you want to use a relay of any other trigger voltage, of any other DC trigger voltage, then you have to do some modification. Are we together? So then, if you have understood, thank you very much, and may God bless you and keep you and keep what you have understood. So you may see that, you may confirm what I told you. When you, Pili, we are in the class. Ruben, we are in the class. Sit as a student, not as a boss. So when you check this relay, you see that it will be written RL1 and 12 volts. So this 12 volts, it's a DC trigger voltage. Okay? So how can we have a relay switch with trigger voltage of 5 volts? Well, we have to double click or we have to right click and edit properties. So what should we edit? We have to change the value of 40 component value. So let us delete 12 and write 5. We just need 5. Okay? So you have 5 volts. After doing that, stop the video and then do it. Have you done it? You do it quickly. Then now we can run our simulation. So in run our simulation, this is cutoff regions of the of the bipolar junction transistor. So in cutoff region, the pole located or connected between common, say common, and normally open, normally closed. Right? So when there is a supply of the trigger voltage of 5 volts, the relay will turn on. So the pole will move from normally closed to normally open. So stop drawing, look on the screen. Look here, hey, look here. So now we are going to turn on the transistor to switch on to operate in saturation region. So for you, just examine the pole. The pole will shift, will move from normally closed to So this is the process. So have you seen? The pole has moved, right? It has disconnected the normally closed contact and connected the normally open. So when we learned about switching time or about operating time, and we say that this relay, the 5 volt relay switch, it can operate, I mean that there's a release time and operating time. And we say it can operate, so it can actually turn on off 300 times. So what do you mean? It means, for instance, if just I hold this one and then just see, you see, so I'm turning on the relay switch and off. Turning on the relay switch and off. So even if I do quickly, there is a delay. If you examine, there's a delay. For me, I will just see pushing this mount quickly, right? But there's a delay. And that delay is what we say that raising, it means that we mentioned about 2 timing. One is 10 milliseconds and the other one is 5 milliseconds. Are we together? Those are the features of 5 volt relay switch. You forgot. Why? Because you want to be a practical electronics engineer who know nothing about theory, or who write theory and keep them aside. Okay, so if that's the case, so right now we thank God. Our relay switch is working. So we can implement it, the last block. Okay, so we still have the last concept that we have to analyze, especially for the relay switch there, and especially in the part of measurements. That's why I told you that measurement is very important in electronics. When you refer the theory, especially workshop 14, I told you, or we learned the features of the 5-volt relay switch. And when we learn those features of the 5-volt relay switch, hello, we are in the class. When we discuss about those features, open the features of a 5-volt relay switch. So when you read the first feature, read the first feature. The DC trigger voltage across the is 5 volt. Then let us go and see the potential drop between the first coil and second coil of the relay switch. It's 4.03 volt. Is 4.03 volt less than 5 volt or equal to 5 volt or greater than to 5 volt? Limi is not in the class. Patricia? It's less than 5 volt. So according to the theory, in case that the minimum or the typical trigger voltage of the relay switch required to trigger the 5 volt relay switch, it's 5 volt. But in these simulations, we see that 4.03 succeeded to trigger the relay switch. So these are the drawbacks or the challenges of the simulation software. But we'll do the same measurements in hardware to verify. Okay? Okay? Take a note, my dear student. Then, read the second feature. The DC trigger or 5 volt relay switch is what? Must 70 milliampere. So let us examine what is our DC trigger current right now. It's 12.0 volt. So first of all, it has changed. Before it was 14.9 milliampere. Now it is 12 milliampere. You have to note something. That's why I told you that there is no any perfect or best simulation software. Because you didn't do anything. You just add another block, then the parameters changes. Okay? So, right now, the collector current is 12 volt. It's 12 milliampere. Is 12 milliampere less than 70 milliampere or equal to 70 milliampere or greater to 70 milliampere? So, if that's the case, according to the manufacturer, what did the manufacturer say? If the DC trigger current is less than 70 milliampere, will the relay trigger or it won't trigger? It won't trigger, but there it is trigger. Those are the key concepts that you have to take a note and to reason why. Okay. As I said, sir, implement the last block. Okay. Okay, now let us implement the last block, which is called the load or loads. We said we are going to have 2 loads. The first one is lamp, the other one is what? DC motor. So this is the lamp. So let us connect the lamp. Let us place the lamp there, and then we have a DC motor, and let us connect our DC or have a DC motor at this point. Limi, go and dress yourself. Again. Okay. Then, if this is the case, what do you say? Say that is good. Right now, we need also some other measuring instrument. What do we need? We need the DC ammeter to measure the current. To measure the current consumed by the loads. To measure the current consumed by the load when they'll be operating. So those are our components. Let us do connection. Come here, Limi. Come and sit here. Quickly. Okay. So now let us connect the lamp with DC ammeter and connect the DC motor with DC ammeter. Then we are going to connect this DC motor with normally with the contact or terminal that we call it normally closed. But remember that the load needs power. And this lamp, it has been written 12 volt. So it needs DC 12 volt or 12 DC voltage. So operating voltage for this lamp, it's 12 volt. It's not AC, it's DC. So if that's the case, we have to go back to the output of our 12 volt linear power supply. So this is the point. So you have to take 12 volt and then so we have to move and connect across what? Across or connect with the DC ammeter that will be measuring the current consumed by the DC motor. So the DC motor is 12 volt and also, 12 volt, mostly it means that typically it's 12 volt. And the lamp also it is DC, 12 volt DC voltage. So if that's the case, what do we say? That is good. We didn't finish our connection. So what didn't we connect? We did not connect the ground to the common, because the load must be connected between the common and the normally closed, or the load must be connected between the common and the normally open. So let us take a ground terminal. So let us connect our ground terminal with the common of the relay switch. So this is our ground terminal. So remember that any load connected to the normally closed, it always run or it always operate without trigger voltage. That's what we discussed in theory. So let us come back. Let us run our simulation. So this is the case when the transistor operates in cutoff region. Okay? Okay? So this is the case when the transistor operates in cutoff region. Remember that we have what? The Bjt transistor digna transistor what? Indicator. So it's off. And you see right now the motor is rotating. What they measure the DC what? Current. It's negative 0.97 ampere. Why it's negative 0.97 ampere? Who can tell us? Because the leads of the DC voltmeter are interchanged. The positive terminal of DC voltmeter is connected with ground, while the negative terminal of DC ammeter, the positive terminal of DC ammeter is connected to the ground, while the negative terminal of DC ammeter is connected to the 12 volt. Right? So simply the driving current of the motor is 0.97 ampere. Gaudens, you are Gaudens. Are we together? Class, are we together? Yes. So remember that, remember that the normally closed does not depend. So when there's a trigger voltage, you see that the load or the motor connected to the normally closed or between the normally closed and common has been disconnected from the power. It's no longer rotating. Are we together? Are we together? Then, let us stop our simulation and then let us keep with our arrangement. Let us connect the negative terminal of the DC ammeter with a 12 volt. And let us connect this terminal of the lamp. Let us connect it with what? Normally open what? Normally open or 5 volt relay switch. Are we together? Sit down. So right now we have finished to connect our load between the common. This load is connected between the common and the normally open. And this load is connected between the normally closed and the common. So let us run our simulation right now. So when you run our simulation, let us start with what? Cut-off region. So that the cut-off region, the motor is working. Okay? And then let us what? Switch our transistor into what? Saturation region. What do we expect? The lamp to turn on. So then here it is. So when there's a trigger voltage, the lamp is on. When there is no trigger voltage, then the motor is on. So you have succeeded. Remember that 12 volt is a lot of voltage compared to 5 volt. So if this is the case, we can have the overview of our overall schematic circuit diagram, and it's very interesting. This is our overall schematic. This is our overall schematic circuit. Circuit diagram. Okay, so that is our overall schematic circuit diagram of what? Simple, automatic, or automated system. Actually, if you don't involve measurements, you could see that, or you could say that, just as simple. It's just as simple. There's a lot of things that are happening there. Another thing that I want to teach you, what if you need just to capture the pictures or the photo of what you have been measuring or what you have been measuring. But remember that another thing that you have to examine, check the parameters have been changed when you have been interfacing one block with another block with another block with another block. This is in simulation. You have also to verify in hardware implementation if the situation is like that or different. So, if this is the case, in case you want to snip it, so you have to come to your search bar and write snipping tool. So write snipping tool. Okay, Limi, write snipping tool. Limi, write snipping tool. Then choose new. After that, you can select the point where you want to do your snipping. Then you release the cursor or the mouse. Then you save. For instance, this one we saved it simple simple auto system. So once you have done that, you can go to the directory where you have saved it. For instance, for myself, I have saved it here, and then I go to, I'm searching the snipping. So where is it? What name did I write? Import. Save. Simple auto system. SI. Yes, this one. So this is the image that I have captured from my simulation. So you can have a number of snipping, and it's better to have them in case you want to use that simulations or the outputs of your simulation in Word documents or in Excel or in PowerPoint or whatever. So my dear students, this is the end of workshop 15. I know that for those who have been slumbering, they are saying thank you God. But these are the assignments that I have to leave. The first assignment, every student in this physical class and online, I ask you to redraw this systematic circuit diagram 3 times. Now we redraw it once. So once you leave this class, you just take a rest after maybe 1 hour, you redraw for the second time from your brain. Don't refer exercise book, don't refer the previous drawing. Then after short times or the next day or the next time, so after 2 hours or 3 hours, you redraw it again. And then you redraw it a third time. After that, I believe that you will learn a lot. The second assignment, you have seen that we had a number of testing points. We used to label them testing point A up to M or N. Go and draw, means that draw the table of results. And in that table of results, it should have 5 columns. Eliakim, I'm talking to you. 5 columns. The first column, testing points. The second column, electric parameters. The third column, theoretical values, theoretical calculated values. The next column, it's what? The first column, testing point. The second one, electric parameter. The third one, calculated or theoretical values. The fourth column, simulated values. And the fifth column is what? Measured value. But in simulated value, in the columns of simulated value, you'll have 2 sub-columns. One column is, okay, I think that, 5 columns are just enough. And make sure that you fill all the cells. Where that you say, in this testing point, we measured base current. You have to read what you have measured and note it. Are we together? From there, we'll verify the concept I've been teaching you and I've been preaching to you, that engineering is all about diagrams, engineering is all about numbers, and engineering is all about tables. In case you say that, okay, just see it means that the relay is working, you don't have any measurement, you don't have any table of results. That is not an engineering experiment. So, if that is clear, I left you 2 assignments. Make sure that you do it. I would like to invite you in the next workshop. That will be workshop 16 where we're building this system physically or in hardware implementation. So I would like to thank God who have given me this chance to teach you, and I would like to thank you who have attended this class. I would like to ask you that in case this video will be made public, make sure that you review several times. One of the challenges that we are facing are the Tanzanian teenagers or Tanzanian students. We always make an assumption that once we have been taught a concept once, we listened, we have learned, we have understood, then we think that that understanding will remain constantly for the long time, while it's not true. So make sure that you take advantage of this video to review this material several times until you master the simple automation system. So thank you very much. Welcome in the next workshop. Bye-bye. I forgot to congratulate you. Okay, let me congratulate you because some of you were unhappy. Some of you did not take lunch. Some of you are slumbering. Some of you, get prepared. 1, 2, 3. Hongera. Imara. Wow. You don't say Hongera, Imara, wow loudly because you are not happy. Thank you very much. Bye-bye.